Hello boys and girls. Usually, of course, I try to do the videos on Wednesdays, but I have such a big stack of topics I want to talk about, so I thought I make this a small bonus video. So in this video, we are looking at the completely formal, i.e. computer checkable proof of this short statement here. This is what we are going to discuss, this proof here, so that we understand it. As you see, I relate back to the Metamath website because they have this normal, by normal I mean like almost textbook first order logic approach, and then standard set theory axioms and everything fully formalized content that you can read online. I have myself not actually looked at the verifier much, but I used a lot of their axioms in my video where I talk about all the axioms of mathematics, in particular because there I have this sort of constructive spin where I start with constructive Zermelo-Fraenkel, go through the propositions and predicate logics and the axioms of set theory, and only at the end add log-x to the middle choice and stronger axioms I discussed as well shortly there. And there I have already made use of the formulations as you find them on Metamath to a large extent as well. And for a while now, I wanted to make a video where I actually step through a fully formal proof that you get a feel kind of for how that looks like. This video also relates to the one I did on predicativity and impredicativity in particular, because there I talk about the one axiom of set theory that we are going to make use of in this video, namely separation and bounded separation at that. So to quickly summarize before we get into the proof, when I talked about impredicativity, right, I talked about classical argument that unrestricted comprehension, where you say, hey, for every proposition that I can cook up, there's a set which has exactly this element. That doesn't work, that leads to this famous Russell paradox or antinomy, and the argument goes involves anyway that you say, okay, if I had unrestricted comprehension, then let's look at the set of all sets that don't contain themselves, and then as I show in that video, you quickly come to this contradiction, right? So you have there somewhere in this proof, like I don't go for it now, but you end up with a contradiction, so a situation where you can prove something and also its negation. Again, another way of getting at that is not to say I have unrestricted comprehension and then I lead to a contradiction, but to say, hey, let's assume I have a set of all sets, including itself. Let's start out with a situation where I have an object which is a set that contains all sets, and then likewise, even with normal subset comprehension, I'll get to a contradiction, right? Instead of having an unrestricted comprehension, which is problematic, it's also problematic to have a set of all sets, and comprehension on that set is like sort of the equivalent situation. And not even doing that, but starting out with just the restricted comprehension, or separation, or in this video bounded separation. You can, from bounded separation, derive the non-existence of this universal set, which is exactly the reason why assuming the universal set and having separation gives a contradiction, right? So the positive part of all these sort of all these scenarios that I just went through is that if you assume that you have bounded separation, which this is like a standard, one of the standard axioms of set theory, is basically in almost all non-super academic studies of any set theory that will have separation, then from that alone you get that there is not a set which for all sets has the property that these sets are in it, and that's what we are going to show, right? So here we have one second here, this is the statement that we are going to get at. So it's not the case that there is some set which has the property that for all sets these sets are in it, right? So if X were the universal set, the set that has all sets, it has the property that for all sets Y is in this set. It's not the case that this is so. So this is what we're going to establish and this is the proof. This is this formal proof that we're going to get through, and then you get a feel for how that looks like. Okay, so of course, subscribe to the channel if you don't have already. Be one of these almost 1,000 lost souls. And recommend the channel and whatnot. Click the bell icon, please. So much for that. Yeah, so as a quick recap, this is this Metamath website where I'm going to show you a few pages today. So for example, here is like, I think that's the page saying that the value of the cosine function at 0 is 1, and then they prove it from what they have. And the nice thing here is you have it says the theory proves that it's provable that this is the case, and then you see the proof. For example, they start out with we take for granted, or we have proven already that 0 is in the real numbers, and then they use some other like steps in the proof. This is this formal proof tree. One condition to the next. You will see like how this functions in a second. Then, and here you can also like look at these intermediate like theorems, lemmas that are used. So for example, here they have that I times 0 is 0. Well, yeah, everything times 0 is 0, right? And if you look there, then you get to that, like, okay, these proofs are all very short, but here, for example, if A is an element of the complex numbers, then the indeed has this property, and then they prove it from like more and more primitive like statements, right? So you can click yourself through these sort of things, and eventually you get just through the logic statements. So for example, here in this proof, eventually down there they use that given, and like this is the hypothesis, this is given, like given the context, so to speak, psi, and you know that phi and psi imply key, then you have that if you just have this, then this follows because this is by a hypothesis already true. It is just a logic statement, and you can then even go further down and eventually you get to the axioms, right? So this is the standard statement. If phi is already true, then for any statement, this statement implies the already true statement. And here you also see then, or what syntax is used, which theorems were used to prove that. For example, here you see modus ponens. Let's look at that. This is basically used by everything. So if this is true and this implies that, then that is true. This is modus ponens, and this is basically used by everything. No surprise there. Let's go a little bit up to something more. Okay, here, for example, here see you have this statement there that in the complex numbers, any complex number multiplied by 0 is 0. And then you see this is proven from these axioms. It starts out with like propositional logic stuff, and then some set theory axioms come in. I don't know, here axiom of separation, extensionality, null set. This is the there is a set which has the property that nothing is in it. This is where the axiom of empty set is used, and then you see that this proof like eventually somewhere down the line relies on these, and you see which other theorems reference that, and so this is like this very like people did this tedious work of proving a lot of stuff super formally, and then you can go also on the website and see how the computer implementation of this looks like. Basically, the computer implementation of this is a reference to all the steps getting there, and then it's computer checked. It's like a GitHub project. Okay. Okay, let me see. How do I proceed? Yeah, so one thing I have not discussed in the video on all the axioms is it's this syntactic rule for boundedness, right? And in like this guy, BJ, I think Ben is his first name, I'm not sure, I saw it on the GitHub page. He has like developed a little bit of constructive Zermelo-Fraenkel, like up to piano axioms proven, or like the construct, like the versions without excluded middle, of course, from set theory, right, using axiom of infinity and proving all the 7 piano axioms and constructive and induction. And so he has formalized some of the features of the constructive theory that I just talked about, which has this boundedness restriction on some of the axioms, in particular on the axiom of separation. So you have the axiom of bounded separation, that where you say, like, I will not like go into detail in this sort of things that I discussed already in the axioms video, but here you say not only do you have like restricted comprehension, where you use comprehension to define sets in terms of their supersets, right? This comprehension scheme also in normal Zermelo-Fraenkel is used to have a property and you have a set, and then you cut out with your cookie cutter new sets as subsets from the already existing set. This is how Russell is resolved there. But here in this formulation, you even demand that this predicate is a bounded predicate, i.e. it doesn't have like these universal quantifiers ranging over the whole domain of discourse. So, and he has this he axiomizes boundedness. This is this symbol. This is like a single like property of properties, if you will. So you say, if I have a bounded expression, and we're going to have a very simple one in this video, then per axiom, this is one of the, I don't know, 10 axioms for sets, this axiom of bounded separation holds. And this is the one axiom that quickly like going to go through here. It says that for all sets holds, this is going to be the supersets, that there is a set, this is going to be the subset of A, such that for everything that is, like for all sets, these sets are exactly in B if they are in A, i.e. B is automatically a subset of A, and they also have fulfilled this particular bounded predicate. So you take an A, you define, like you have sort of characteristic function essentially. You cut out, like with cookie cutter, you say, oh, this is what I want, this is not what I want. And so you get, by this axiom, the existence is granted of subsets of A that fulfill this phi, okay? And this has to be bounded. I mean, we are not going to make use of essential use of the boundedness in this video, but it just happens to go through with boundedness as well. Okay, so that's that. What we are going to see is basically we are going to choose a particular predicate that we're interested in, and then we have the fact that this holds, and we're going to use this expression a little bit. Okay. So I talked about the fact that this is in constructive Zermelo-Fraenkel, and this is the proof, and it has 17 steps. The same actual proof also exists for Zermelo-Fraenkel even on Metamath. So this one is the same thing, except this has 15 steps. I think it's the exact same steps, but they just don't have these two boundedness clauses there, which are required by the bounded separation axiom. So we could just as well look at this one, but like it even works with the more restricted axiom. So this is the same thing. Here I think this is a little bit more concise in terms of the axioms, because it's like easier to state classical axioms, because you don't have to watch out for implying excluded middle. And here you say the only axiom here used is the separation axiom. There is this one thing that I don't quite understand, why here at the bottom extensionality is also listed, but that might be a feature of this so-called math box. Like it is the math box of PJ. This is like is his user space of this guy, and so maybe that's just creeped in somehow, because I don't think it's necessary. Because also for the classical proof, it's obviously not necessary. So I think it's safe to say this is just using separation. But I pointed out because I was not sure about this. Okay. If you want to check this out in the computerized version, here is this BJ null set. This is the name of this theorem. As you see here, this is the name, right? Maybe we can find out what it means. Yeah, no set contains all sets. This is the abbreviation for that. And here on this is on GitHub, as you see. This is actually the proof of here. Just like this line and this second line, and I think this is the code from that. So here you see the sequence of steps that the checker reads in and verifies, and this is how then in practice in Metamath this is written. I mean, I think this is a project from the 90s, end of the 90s, and of course it's not very hip, more like programming language approaches and type theory, maybe even more in vogue, I assume. I think it's like a few dozen people working on Metamath. And so that looks like that. This is in this big file with these proofs, and this is the box of this guy, and so that's just FYI. That's how it looks there. In the machine check. Okay, here again, this is the math box of this guy where he discusses this boundedness axioms, these syntactic axioms to introduce the boundedness notion, to formalize that. But this is super like trivial from a logical perspective. He has, for example, these axioms to say, oh, if I have one bounded predicate and also another, then the conjunction of them is also bounded, right? I mean, everything will be bounded unless you come along with the like quantifiers like that. And here, for example, if this is a bounded predicate, and then if you bind x in it, but with respect to a subset, so this is still bounded because you are just quantifying over a bounded subset y. And so there are some basic axioms, and this is like this additional stuff that's introduced by him here. Okay, and now before we get through the proof, and I hope I can get it done before 40 minutes, I will show you like the main axioms or in between lemmas and theorems that I actually made use of in the final proof then, okay? So here you'll see this is like really like easy, right? So if this is bounded, then the negation is also bounded, right? Because the negation doesn't introduce any like quantifier, like any impredicative notions. So, okay, easy peasy. Similarly, the statement x and y is a bounded statement. Okay. Then contraposition will be used. So if phi implies psi implies key, then you can switch those around, right? This is contraposition is valid constructively, even like some other statement that just imply this would be provable constructively, but this is like, if you can negate. You cannot go in the other way around constructively, but you can do this. So this is, as you see, on the intuitionistic side. So this is going to make use of. And as you see, this is here not taken as an axiom, that this is derived from some other statement. So we could not track this down. What this is, like this is proven from 5 logical axioms. Like, let's take a look at one. So here, this is an axiom. I discussed this axiom and among others in the axioms video. So here it says, if a proposition implies its negation, right, then this is like an inconsistent proposition, so can't be true. So this is like one of the what's it called here? Yeah, negation introduction. So this is one of the axioms, and that's how we roll here. Okay, then yeah, this is basically the contraposition, but not with an implication, but with a B implication, right? So you can do it, of course, in both directions. If you have both directions, you can flip in both sides as well. So you can introduce negations if you have this sort of situation. And you see always here, these are like all conditional, like this. They leave room for all the statements being done with this something implies blah blah blah, and then they're actually only interested in whatever happens here, and it's not much affected by the whatever context you have here. Okay, this is just a side note. When I explain these formulas, then it suffices if you just look at them and think about them here. Okay, and this is a sort of interleaving situation. If you have that this implies that these are equivalent and also these are equivalent, then you can say if I have both of these, then this is equivalent to this. Like I hope it makes logical sense, right? If you have this is equivalent to that and this is equivalent to that, then those together are equivalent to those together. Okay, it's not a big surprise here, but it is then formally proven as well from some other axioms, logical axioms. And similarly, this is basically the same statement, but not with a conjunction, but with a B implication here. Okay. Will be made use of, as you will see. Okay, this is a little bit more interesting. This is a sort of, I would say, disjunctive syllogism, is I think the name. So what we have here is that if this statement is equivalent to its negation and this, right? If this is equivalent, well, this is an inconsistent situation, right? Because this implies its negation and the other way around as well, right? So whatever, like this is an inconsistent situation. So whatever side would be true, then this would also be true, because this is this conjunction is a positive operation, right? For example, that being true would imply a contradiction, and that this is also the case, and therefore you get everything again, and in particular, either you can view that explosion implies everything, or yeah, that's basically it, right? This is basically the argument. This is like conjunctive part of this contradictory statement. So you can reject it. You can basically you have this in this package of this inconsistent situation. This is what will also pop up in our proof with set that contains itself, blah blah blah. And if you're interested in the proof, oh my god, that's even 30 lines long, even if it's so like just involving propositional statements, but you can actually see how you derive it, and this comes from even 7 axioms. Okay, then okay, these are this sort of forwarding proposition. So if phi implies psi and psi implies he, then phi implies he, right? You can like go over psi and like kick it out as a forward, go from this directly to this, because this is a chain of inferences. Okay, it's easy enough. I think this is similar. So this is basically the same thing, except with B implications again. And this is similar. So here, if you have one x that validates this, and you have the situation that the phi implies psi for any x, then you also have an x that validates this, right? This is also like a kind of forwarding. Okay, and here it's like, again, sort of forwarding. Like if you know that if this is true for all, then psi is true, and this is true unconditionally. Like in Metamath, there are no argument brackets, which is maybe why this is a little bit hard for you to read. Like now we're talking about predicates, but the arguments are hidden. But basically you think of x potentially being like part of this expression, but it holds, like if this holds for all x, then this is true. If you write it just down like this, then this means it is the case. Whatever x you, like meta variables in this language, whatever x you plug in, well, then you can also by this statement get the antecedent, like consequent. I don't know the Latin word so well, but the result anyhow. Okay. And then finally, and this is a little bit more complicated, because again, it gets a little bit difficult there with the hidden variables if you're not used to that. If you go on the main page on the first side, I will show you that in a second. Then you can read up all like the usage of these propositions. At least they have the substitution hints here. So here we have the situation that assuming in the case where x equals to y, in these propositions, like read phi as phi of x and y, and read psi of y, then in the case that they are, like if I have given that in the case where they are the same, you have this implication. Then if you have the case that phi holds for all x, and also you have like this global for all y in a meta variable, like this is not written there, but this might depend also on y. So if you have for all y, you have also the situation that if this holds for all x, then through the, like in particular, through this like making use of this hypothesis, you can also get this with free y. Okay, so this is also again a sort of forwarding, and this is then the right. Is this the axiom already? These are other variants where they have, well, let's not get too complicated. This is the symbol for x is constant with respect to the x argument, and there are various formulations. But in the end, this is also kind of forwarding. We're getting rid of this equal sign here, but we have a sort of stronger condition, like that it holds for all, and then in particular we can use this situation to get there. Okay, I don't want to get too much lost here because I'm already explaining the bare logic for too long. But this is the step that we're going to use to get from an equality sign to this all quantifier. Okay, I will also close this, and I have written down like some notes on the arguments that you will see in a second here. I have went through the steps here, and I will put it in the GIS below. But so with that said, let's actually step through the proof. I will again. What we are going to prove is this here. We're going to prove that it's not the case that there exists an X that's the 2B universal set that has the property that for all y's are in it. Right. It's not the case that there's a universal set. Is what this is saying. And the proof, maybe I can barely fit it on one page, but you see here this has these 70 steps, and if you're like you have to stare at it a little bit and to figure it out, but finally once you've done it for some minutes, then it actually makes, like, it's actually not that hard. So I will first like shortly discuss them in a non-linear fashion, and then at the end we might again go through them. Okay, so the first thing that I want to point out is that so here this is what we want to prove, right? This is the statement that we want to prove, and the first step is to realize that this thing, what we want to prove, is actually implied by this thing, and therefore what we really want to do in the proof is actually prove that thing, because in one step it implies that. Okay, and what are these statements? Well, okay, again, this, what we're going to, like the final statement that we arrive here, that is stated here, says it's not the case that there exists a set that has all sets. And another version of saying that implies it, like it's, no, don't want to say equivalent, but in any case it implies it, is following that for all set, there is some set. This is a stronger statement. For all sets, there is another set that is not in X, right? This logically implies that there is no set which has all sets. If you know that for all sets it is the case that there exists one that is not in it, right? Then in particular there is no which has all. So this is what we're really going to end up with, and we're going to end up with it here in the last step. This is here, sorry, in the second to last step, and then with the first step here, we're going to get to the end. So this is the statement. Again, the you don't see the x. Sorry, this sadly it doesn't fit on one screen. But here the x is missing. The for all x is missing. But in Metamath you have this meta variable where you can think of them as universally closed. You can say for all variables this thing holds. So if you don't see a quantifier for x, then think of it as universally with a universal for all. This implies this by this step 1. So we want to get at that. And how do we get to the existence of a set with a certain property? Well, we use the one axiom that we grant ourselves that has the claims existence, right? We're going to use bounded separation, which says that for every set, blah, 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 there exists some set. This y is the one that will exist. So we want to use bounded separation with this sort of property, right? So, and if you recall, like bounded separation looks like so. This is the phi in the bounded separation. This is a predicate, but the bounded separation says for all sets x, there exists a set y such that for all elements in it, these elements are exactly in the subset of x if a certain property holds for the elements and potentially making use of x, and this is the predicate here, right? So let me just do the comparison. I will go to this page for a second. So this was the axiom, right? The bounded property that we are going to assume is this statement, which is a conjunction of element relations and negation. So this is obviously bounded. It doesn't even have any quantifier, not even a bounded one. This is just a statement with 3 variables. And here, this is exactly the scheme of the bounded separation. Exists for all are in it such that this is exactly this sort of scheme. Okay, so we're going to use this existence statement here. In this case, this is going to be the thing that is true by the axiom. This is exactly this statement, and we want to prove that this statement, which is true by the axiom, implies this thing, which is exactly what we want to get at, right? We have then by the axiom of separation, there exists a y that has this property, and once we have proven that this property implies this property, then we have proven that there exists a y which has that property, and then with 1 we have proven that. Okay, so what we want to get at is that statement, right? I repeat, we want to prove this statement because we will get that from the axiom, and once we have proven this statement and the axiom, then we get this statement, which is exactly what we want here to imply what we actually want to prove. Okay, and remember when I just a moment ago explained this syllogism, where if you have a situation with something that is contradictory and then with the conjunction statement in between, then you can negate the statement in between. This is also what happens here. So this statement is derived from, if I had to highlight this, so this is the same thing, and here is just a more complicated one statement with this statement is here in the middle, and here is a contradiction. Here says y is in y, and here not y is in y, and so this derives with the, I think this is this one, with this, the just propositional claim. Yeah, this is this one, right? So this will be y is in y. This is not y is in y. Then we will get this. Okay, and this is just an in-between step. This is just exactly this step. So actually, now I've argued that we want just that this, which is granted by the axiom, implies that thing, right? So this is actually now what we want to get at, right? We want to get, and now I can fit it on one page. We're done once we have shown that this holds true. And to get at that, we just need basic equality statements You know, all the statements that I have not covered now are just these 8 statements. They are all of the form if z equals y then something. And how do we get to this statement? Like we don't like as humans we don't learn much from this because it's like a very long expression now. It's not very like intuitive. But here we get with like this is actually like formally trivial, even though getting there like in this very short way is kind of, you think about, oh sorry, I covered this up, that's not good, oh damn, I hope I didn't cover up too much of this. Happens sometimes, but I think the logic is clear, right? I just said that this statement is obtained by that statement. This thing is negated here, and here is this contradictory y's and y. Okay, sorry for this covering. So this is what we want to get at. How do we get there? Okay, now looks like so. Here we have a list of basically 4 or 5 statements which are really entirely trivial. It says if z equals y, then z is in y is equivalent to y is in y. Right? So basically, if this is true, if z is just y, then you can replace any z on this side with a y. Then it just says y is y implies y is y. This is like a tautology. And similar here, like for example, if z equals y, then z is in z. It's the same statement as y is in z, right? Take this here, replace all z's with y, and then it's just a tautology. And these are all of this form. Like all these statements are of this form. Like if you use here the substitution of equality, this is what equality gives you, then this is just true. Okay, and here then, let me see which one is used here, because it also looks sort of trivial, but okay. And here they now like this is where you get rid of the in-between step, right? This is what happens. This is what happens here. This is what happens here in this step now. So 7 and 8, these statements are used, but this one is eliminated. I will highlight this for. So this one is eliminated, and then we get that this equality implies z in z is the same as y and y, and you get this. But also, like for you, it's also trivial, right? Just by substitution, if you take this thing and replace all sets with y, then it's clear. Okay, and similarly, this is the double, like the contraposited statement. We have also seen that this is just goes from 9 to 10 with this. And the other 2 statements are these interleaving statements that I talked about, right? So I said that if you have these statements, then you can say, oh, having both of those isn't the same as having both of those. You interleave them and you clash them together. And so what here happens here is then that similar, you use 6 and 10 and interleave them with this conjunction. And very similarly, now you take this thing, you take 11 and 5, which is this one, and interleave this again, and then you get this long statement here. Get the final one with the equality. And now we're going to use this this one where you pass from equality to the for all statement. Let's have a look at this again. This is a version of it anyway, right? This was where I explained you have equality, but then you look at these sort of special cases, and you get from equality, you get rid of the equality, and you have a universal quantifier. And this is what happens here. You get there, and of course I presented this as a very like formal step. Like this is just clashed in together these ugly symbols. But now we have this statement, right? And then from here we go. Here like we have exactly like composited and interleaved the statement that here we can then eliminate this thing because that is in contradiction with this one. We leave with that. Then this is an in-between step. We get this quantifier here, like this is getting from there to there with this in-between step. And then by axiom of separation, this is true, so this is true, so there exists a y such that for any x there exists a y such that y is not an x. And then finally, by this logical relation, I have not even shown you that, but I mean, it's also sort of, this is true constructively, right? If you have that for all something exists, then I can write down a lambda calculus proof of this as well, like easily constructively, and then we're there, and you see we have just used separation, and we find that it can't be the case that there is a universal set. And I would also say, like, it's not necessarily easy that you, or clear that you learn anything from this way of doing it, because you have these ugly in between steps. But there you get to the sort of minimal positive statement, right? Just assuming the axiom follows something, and having that, all like these paradoxes, like you have this statement is much stronger in a way than the paradox statement, because now you can see, like, assuming even separate, like this bounded, restricted separation, you get this statement. So if this statement were true, if it were true that there was a universal set such that all sets Y are in it, it's not consistent with bounded, restricted separation. This is the core, that's the positive part in a way of this anatomy. Not that I would have seen that this is provable just from that. There's also, like, very informally, you can also argue like that, assuming that power set axiom, then like you can use Cantor as a much stronger statement. The O no set has an surjection is into its power set. So if there were a universal set, then the power set of the universal set, which exists by the axiom of power set, could not be surjected into. But if it's already the set of all sets, right, then the identity would be a surjection, and so you have the contradiction as well. Okay, so 40 minutes, I was more or less in the time I wanted. But now you see how this fully formalized proof looks like. I might do this once again, because I'm personally interested in seeing how the constructive piano axioms are derived from the set F, constructive Zermelo-Fraenkel. And I will look at that, and if I find it interesting and don't have any better videos to do, I will also cover that and report how that looks like. Okay, have a good evening and good night.